Today we're going to talk about rates of change and tangent lines. As a warm-up, find the average rate of change on the interval 1 to 4 for each of the following functions. Press pause on this and then try to do this yourself. See if you can remember how to do this from pre-calculus or even algebra 1, understanding what an algebra rate of, or an average rate of change is. And then I'll give you about 5 seconds, press pause, try this, and then I'll come back and show you the answers. So for problem A, you take f of 4 minus f of 1 over 4 minus 1. That ends up being 31 minus 1 over 3, which is 30 over 3. For part B, we have f of x equals x cubed minus 8. We once again do f of 4 minus f of 1 over 4 minus 1. We get 56 plus 7 over 3, which is 63 thirds, or 21. Therefore, the average rate of change for a nonlinear function is the slope of the secant line. The slope of the secant line. The method that we use, if we are given an interval from a to b, we find the slope, which is y minus y over x minus x. So we have f of b minus f of a over b minus a. Once again, that's something that we've done ever since algebra 1 when we were finding slopes. We would do y minus y over x minus x. However, now we're going to start talking about instantaneous rate of change. So an instantaneous rate of change for a nonlinear function is the slope of the tangent line. And there are several methods to do this. So if we're talking about the slope of a tangent line, we're going to talk next chapter more generally about the slope of the tangent line at any particular value, or the overall slope of the tangent line, or what we will end up calling the derivative of a function at any value. But we're talking about at a specific point. Okay, so in this particular case, we're talking about the slope of a tangent line at one particular point. Okay, so we have method 1, which is the limit as h approaches 0 of f of a plus h minus f of a all over h. Or method 2, the limit as x approaches a of f of x minus f of a over x minus a. Now, in honors pre-calculus last year, you might have learned that this is called the definition of the derivative. But even if that's not something you learned, this is something that you practiced a couple times when you started learning limits, and they may have snuck these in. These are actually definitions of the derivative. Method 2 is actually the definition of the derivative at a point. Method 1 is the definition of the derivative in general, but you can use it at a point as well. So most of this notes sheet, I'm going to only use method 2, but in example 1, I will use both methods. And then once we get to chapter 3, we'll be using method 1 more extensively when we're not talking about it just at a particular point, when we're trying to find the slope of the tangent line at any particular point, or what we will call the derivative. Okay, so example 1. Oh yeah, by the way, for both methods, a in this is the x value of the point. So if the point is a comma f of a is the x value, and then f of a is the y value. So we're going to find the slope of the tangent to the parabola, f of x equals 2x squared minus 1 at the point 2, 7, and then write an equation for the tangent line. Okay, I have to cover that up because it's part of method 2. So if we're looking at method 1, the first thing we will do is we will have the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Notice that that's just taking the formula and replacing a with the value of a, which in this problem is at 2. Okay, next we have just replacing f of 2 plus h and f of 2 with the actual values of what those are. So we're replacing them with the function 2x squared minus 1. So notice that 2 plus h goes in where x was, and 2 goes in where x was in the other part. Okay, then we have the limit as h approaches 0, and I just did some algebra. We're multiplying things out, then doing a little distributing, combining like terms. Notice that there's an 8 and a 1 and a -8 and a 1. So everything ends up canceling out. That's something that you'll notice in method 1. In method 1, if you're doing this right, you should always end up with every term in the numerator having an h in it. If you don't end up with every term in the numerator having an h in it, so then everything cancels out, there's a problem. Okay, so then I have the limit as h approaches 0 of 8h plus 2h squared all over h. And then I do a little combining and so on, canceling the h's out, sorry. And then I just substitute 0 in for h, and I end up with 8. So that's the slope. My slope is 8. And so since my slope is 8, I'm now ready to write the equation of a tangent line. And the equation of my tangent line is y minus 7 equals 8 times x minus 2, because remember the point is 2 comma 7. Okay, so here is the entire method 1 shown. I'll show it for about 5 seconds. You can press pause if you need to uh, take things into consideration. Okay, now in method 2, something that's important to note is if you do it correctly, the denominator will always cancel out. Okay, so in method 1, I forgot to write this when I was doing this, but in method 1, um, all of the terms that don't have h cancel out. In method 2, when we're talking about the definition of the derivative at a point or the slope of a tangent line at a point, we're going to end up where the denominator will always cancel out if we do it correctly. Okay, so I just rewrote this with 2 replacing h. Then I replaced f of x with 2x squared minus 1 and f of 2 with 7, because those are true statements from the example, from the problem. Then I combine like terms. Then, if you notice, I factored out a 2, and then I ended up factoring x squared minus 4. So notice the x minus 2's cancel. The denominator always canceled, which is good. Now I just substitute 2 in and I get 8. So either way, I got 8 as my answer. Example 2, a water balloon dropped from a window high above the ground falls y equals 4.9 t squared meters in t seconds. Find the balloon's average speed during the first 3 seconds of the fall. So the average speed during the first 3 seconds of the fall, that's just the slope of the secant line. So f of 3 minus f of 0 over 3 minus 0. That's f of b minus f of a over b minus a. That equals 4.9 times 3 squared over 3, which is 4.9 times 9 over 3. So that's 44.1 divided by 3, or 14.7 meters per second. Now, one thing you could note is that if this is a no calculator problem, you actually could have recognized that you could have canceled one of the 3's out, and then that's a little bit easier to multiply together. So the speed at instant t equals 3. So the limit as t approaches 3 of f of t minus f of 3 over t minus 3. I'm just doing method 2 like I said I would. So I replace f of t with 4.9 t squared. I replace f of 3 with 4.9 times 3 squared. Remember, the denominator has to cancel. So the easiest way to do this problem is to just factor out a 4.9. And then I end up with t squared minus 3 squared, or t squared minus 9. That's the difference of 2 perfect squares. So I end up with 4.9 times t plus 3 times t minus 3. Notice those cancel out. And I end up with 4.9 times t plus 3. And that's inside of, and then I just substitute the 3 in, and I end up with 4.9 times 6, which is 29.4 meters per second. One thing I forgot to mention earlier, and I should have, is notice that all of these limit signs are being written very carefully. I forgot to slide this off. So notice in example 1, a was equal to 2, and you have to write the limit notation very diligently. So notice I keep the limit until I actually substitute the 3 in. Just like earlier, I was keeping the limit around until I substituted the 0 in, and I kept the limit around until I substituted the 2 in. So that's just something to keep in mind. Example 3, find the slope and equation of the tangent and normal lines to f of x equals x squared plus 1 at the given point. So I'm going to use method 2. I'm going to substitute x squared plus 1 and 10 in for f of x and f of 3. I simplify. I recognize that x squared minus 9 factors. And then I end up with the limit as x approaches 3 of x plus 3, which I then can directly substitute 3 in and get 6. So notice once again the denominator canceled. Number 4, determine whether f of x has a tangent at x equals 0. Oh, my fault. Example 3, I forgot to give you the equation of the tangent and normal lines. So since this has the point 310 and I have the slope of 6, I can then write the equation of a tangent line, and here I can write the equation of the normal line. One more thing to point out, I forgot to mention it on example 1, but notice that since the slope was 8 in both problems, that means the tangent line could have been derived using either method. Example 4, determine whether f of x has a tangent at x equals 0. If it does, what is it? If it doesn't, why not? So let's think about this for a second. If something has a tangent, that means that there's a line that can barely glaze the function without crossing it twice. Okay, so for something to have a tangent line, algebraically speaking, the limit as x approaches a of f of x minus f of a over x minus a has to exist. It has to work. I could have used method 1, but once again, I'm using method 2 just for simplicity's sake. So that means that the limit as x approaches a from the left must equal the limit as x approaches a from the right, because I know that's true about limits. If the limit exists, that means the limit has to exist and to be equal from both the left and the right. So that's something to keep in mind. Also, it must be continuous if that's something that's actually going to be true. Okay, so that means that the function must be continuous at that point, or else you clearly won't have a tangent line in that case. So in order to make sure that the function is continuous, you just substitute 0 in, and you get uh, f of 0 equals 0 for both cases. Therefore, the tangent line works. Or I'm sorry, not the tangent line, but the equation is continuous. So let's check the left. If I look at the left side, I end up getting um, the limit as x approaches 0 from the left is -1. Notice that when I substituted in for f of x from the left, I substituted in negative x, because when you look at the function, f of x equals -x at that value. But when I'm doing this from the right, f of x is actually going to be x squared minus x, because that's what happens when we're approaching it from the right. So as I continue, I end up figuring out that the limit as x approaches 0 from the right is also equal to -1. So since the limit as x approaches a from the left is equal to the limit as x approaches a from the right, and the function is continuous, therefore the slope of my tangent line would be equal from both sides, and the function is equal to that value. Therefore, I can actually draw a tangent line. So I have a tangent line, and it's y equals -x, because the point is 0, 0, and the slope is 1. So that's my line. If I'm looking at this, this is what the graph would look like. So if I looked at the first equation, the tangent line at 0 would be y equals -x, which clearly goes right on top of it. And if I look at the other equation, x squared minus x, the tangent line perfectly matches in the exact same spot. So if I have the actual function, that tangent line seems to work perfectly.